Well, we were discussing the chemistry of the phenolic compounds in a little more detail, and these are the main headings in the notes that you had passed out. We're going to leave much of this discussion to your reading the notes. It's fairly important from a test tube viewpoint, a laboratory viewpoint, but not so important from understanding the kind of biological reactions we're concerned with, so I'll minimize that in order not to get any further behind. We were discussing the acidity, and I'd like to pick up, looking at the table on page 5 of your notes. We had said that the inductive effect was an important one, and it could be highly influenced by other effects, but perhaps it's the most easily predicted. And this table of dipole moments on page 5 gives actual numbers of a dipole moment. A dipole moment is a constant or a value that can be determined experimentally based on dielectric constant and some experimental details that we needn't worry about, so that these numbers give some idea of the polarizing effect of the particular structures that are there. The higher the number, the more polarized, and by polarized we would mean it would influence the electronic character of the molecule, so that one end becomes, or one part of the dipole becomes relatively positive, and the other part of the dipole becomes relatively negative. And we haven't put any sign on this because the dipole can be in either direction as far as experimental measurement, but they would be more or less opposite in the sense that the left-hand column is the electron attracting groups, and the right-hand the electron repelling groups. And you've had such tables before without maybe realizing it in talking about directive effects in aromatic substitution in organic chemistry. For instance, then, those groups which attract electrons withdraw them from the associated phenolic groups in the aromatic ring, and therefore would increase the phenolic acidity. As we've indicated, if the electrons are withdrawn from the phenolic OH, then obviously an H plus can escape more readily, and therefore it becomes more acidic. As a consequence, then these other factors apply. It deactivates the ring in terms of electrophilic substitution, at least. This group that withdraws electrons or attracts electrons away from the phenolic group would be meta-directing, except for the halogens. The halogens are still ortho-para-directing, and if you've forgotten what the X means, that's a general code for halogen atoms. And they would favor nucleophilic substitution then. Since they disfavor electrophilic, it would make sense that they'd favor nucleophilic substitution. The phenolate ion would be relatively stabilized once formed, and the basicity of the phenolate would be decreased. So all these things go hand in hand, and it'd be opposite for the other group, which decreases phenol acidity. So you might read that over a time or two and study it a little bit so it's fairly clear in your mind. Now, you needn't remember all of these different substances. Part of the reason I gave you the table was so you could easily refer to it. But if you look at the tables, you'll notice that there are groups that we needn't be too concerned, generally speaking, in ordinary biochemistry, and then others that we should be concerned with. So in the electron attracting group, the carbonyl types and the acetyl types, the ester types and the carboxyl types are about the only four we need to be very concerned about, because the other substituents don't commonly occur in biochemical systems. And in the electron repelling group, the OHs, perhaps the amino, although in our case we're not going to spend much time talking about nitrogen substituted phenols, and the methoxys and alkyls such as methyl, and the aromatics such as the substituted phenyl types would be those to be remembered. And in simple terms then, we can say generally anything with a carbonyl group, because you notice that the carboxyl has what might be considered a carbonyl. If we draw a carboxyl this way, then it has a carbonyl type unit, and an ester the same way. It still has a carbonyl type unit. The aldehyde is a carbonyl, and the ketone, or the substituted side chain carbonyl compound would obviously be the same. So all of the compounds we need to be very concerned about in the electron attracting sense should be carbonyl derivatives, and those that we are mainly concerned with in the electron repelling sense would be either OH or the methyl or similar ethers thereof, and the aliphatic or aromatic substituents. So that if we see a phenol then with, say we have this phenol, or an ordinary phenol, if we had a methyl group here, then we would expect that methyl group to be electron repelling and make the phenolic hydrogen less acidic. So methyl substituted phenol would be less acidic than plain phenol. And the same would be true if we put on a second OH. Of course, you need to consider if there are two OHs in a phenol, then there's possible for either of them to ionize, so that there's a conceivable effect in addition to having the phenol substitution. But if we put on a methyl group, then we wouldn't have that problem, so that this OH would again be less acidic if we substituted with a methoxy group on the ring, or a methoxy structure. So anytime you see this kind of substitution, you'd expect the phenol to be decreased in acidity. Anytime you see a carbonyl-derived, carbonyl if you're from Australia, derived structure, you'd expect it to be more acidic. And those would be the kinds of structures we'd be mostly concerned with. We've already given you an example, but let's look at the table on page 4, the salicylic acid series, which we mentioned the other day. Now, under salicylic acid, you notice two pKs, one in parentheses, which is 3, which would be the acidity or pK of the carboxyl group. So, of course, when you have a carboxyl group present, the compound is acidic owing to that. But if we look at the other pK, the pK of the OH group would be 13.4 in the case of salicylic acid, which is the orthohydroxybenzoic acid, whereas metahydroxybenzoic, just below it, is a good deal more acidic with a pK of 9.9 for the OH, and the para is most acidic with 9.32. Now, we mentioned that the inductive effect then would be expected to, since we're substituting with a carboxyl, we would expect the electrons to be attracted away and the hydrogen more easily escapes, so it should have increased the acidity. Well, if you compare with phenol itself, the metahydroxybenzoic acid's about neutral. In other words, it has about the same acidity as you'd expect without substitution. Whereas in the para position, we do have an slightly increased acidity due to the inductive effect. On the other hand, the ortho position suppresses the hydrogen removal because of hydrogen bonding between the carbonyl and the carboxyl and the OH hydrogen, so that you notice that the carboxyl is made more acidic, but the hydroxyl of salicylic acid is made less acidic. And I'm reiterating something that we mentioned before, but I thought it was preferable to look at actual experimental numbers. The influence of these various substituent groups can be used to estimate the acidity of different phenols. And turning back to page 3, we've made a list of some ideas as to how this might have some bearing in predicting the acidity of natural phenols. Perhaps before we go into this, I might say, why are we interested in predicting the acidity of phenols? Well, you'll see that the acidity has a great deal to do with hydrogen bond strength and oxidation. And of course, we're very concerned in the natural system, particularly in wine, with Browning reactions and so forth that depend on oxidation. So if we know the acidity, which I'm going to show you we can predict to some extent, then we have extra information on the hydrogen bonding and oxidation, which will be important in the reactions that we want to understand in wines and food products in general. Well, we've already indicated the item 4A in the sense the more acidic phenols are the carbonyl substituted generally, and the less acidic are the alkyl substituted, or the aromatic substituted. or the phenolic OH and methoxy substituted. The polyphenols would have a sequence of ionization, and this would affect the ionization of the following groups. For instance, the example given in your notes, if we add hexahydroxybenzene, all of the OHs initially are equal, and you'd expect, and in fact the pK is reported to be 9. On the other hand, as soon as you ionize one, then there's no longer equivalent. And if you had the oxidized quinone form, which is drawn beside it, you see that then it is no longer an aromatic substance, not strictly speaking a phenol, but it's still enolic, and the pKs become much more acidic, but not equivalent. So ionization of the first one would be relatively easy, but the second one would become more difficult. And which was first and which was second would be somewhat academic, since initially they're all the same. In other words, how would you distinguish between the OH groups on the benzoquinone derivative? Well, you can't at first, but as soon as one's ionized, then the rest of them are no longer equivalent because they're either nearer or further from the ionized phenol and so on. True that electron migration would tend to smear this around the ring. Nevertheless, it is possible to titrate it and show two different kinds of acidic functions with a rather acidic pK and a slightly less, but still much higher than the usual phenol, so that it indicates at least that the environment and the second ionization can sometimes be a surprise if you don't think it through. The 5-hydroxyflavone, now let's talk about flavonoids and how they ionize. The 5 position is almost cryptophenolic in many substances in that it is difficult to ionize. So if we have a compound of the flavone series with the 5-OH, then this OH is so strongly hydrogen bonded and it's held so closely aligned with the carbonyl in the 4 position that the 5-OH does not behave as a normal phenol very readily. So this is difficult to ionize, and in fact such compounds will not dissolve even in sodium hydroxide in many cases, so that they are basically very difficult to show that they have any acidic character at all, because of the hydrogen bonding with the adjacent carbonyl, adjacent in the peri sense. Remember, I think we mentioned this, that when you have 2 fused rings, the points of the rings are considered in the peri location, and this would make, you see, 1, 2, 3, 4, 5, and counting the hydrogen, a 6-membered bonded structure. So 5 or 6-membered rings are relatively stable. The OH group would be held in close proximity to the carbonyl, and this would tend to make it very hard to remove this hydrogen as an ionized hydrogen ion. Also, another point we might as well bring up at this stage, while we said that structures with some double bond character of this general type in a phenol, where you have a relatively negative and a relatively positive type contribution to resonance and therefore have charge separation, we said these would make a minor contribution. But the contribution isn't 0, and if you visualize back through the structures, if you have some double bond character to this carbon to oxygen bond, then this will throw the hydrogen into the plane of the ring, so that this molecule would have a tendency to become overall planar with the OH in the plane of the blackboard, and that makes, again, the hydrogen closely aligned with the oxygen and rather strongly bonded. That being so, then in flavones of this type, the 5-OH is very weakly ionized. Now, taking that as a criterion, it's interesting to note that we can use some such facts to learn something about the relative acidity of the phenols in the flavonoid type structure. For instance, 7 and 4' flavonol is soluble in sodium bicarbonate, and we said that most phenols are not soluble in sodium bicarbonate because they're not sufficiently alkaline, or acidic rather, to displace the sodium from the bicarbonate ion. The pKs would have to be more acidic than the first ionization of carbonic acid to do this. Well, if the 7,4' flavonol is that acidic, then it means that the 4' or the 7 is quite acidic, and it turns out that they're both rather acidic. And the best data I'm aware of is referred to here from a paper by Howard and Wender, as old as it is, 1952. I don't know of any further studies in this area, but they studied 2 compounds, and if we take those 2 compounds and compare their results, I think we can pretty much see what the ionization forms and the relative reactivity of compounds in the flavonol series, at least, would be. And they studied glycosides in the 3 position in the quercetin series. And if you, there is a correction on at least some of the copies of the notes. You see where it says Howard and Wender, come down the 5th line, starts off 7, comma, and 10.9, just cross off the 7, comma. In other words, there are only 2 pKs for xanthoramnin, 8.6 and 10.9. Well, xanthoramnin has the 7 position in the form of the methoxy, so it cannot contribute. The 7 then would be gone, and we don't have an ionization constant for that. And in the case of rutin, which is quercetin with the sugar in the 3 position, and xanthoramnin has sugar in the 3 position also, has 7.4, 8.7, 12.6, and 14.2 pKs. All right, putting that together with the information from methylations, which shows that methylations occur on the more acidic OH first, and they show that the sequence is 7, more acidic than 4', more acidic than 3', and then 3 and 5 may be not methylatable. Then it would indicate that the pKs of the different OHs in this kind of structure would be in this order, with the 7 position then being the highest, and the only value we had was 7.4. So the pK of the 7 would be 7.4 in that model system anyway. The next most acidic would be the 4', and we had the 2 values, 8.6 and 8.7 for the 4' OH. The 3' OH would be next, which was 10.9 and 12.6 in the 2 examples of the compounds. And then that would leave this one, and in the case of xanthoramnin, it didn't ionize at all, and in the case of the other one, it was 14.2, in other words, very high, about like an alcohol. Well, that would give you then the expected sequence, and I think it's pretty well predictable in some senses of the word. If we analyzed it further and spent more time, I think you'd agree that besides the experimental data proving that this is so, certainly this one we'd expect to be low. This one you might expect to be high. It has a carbonyl attached if you want to look at it that way, so that's one reason that it would be high. Whereas this one has a glycoside enol, which is a different type of substitution, and the only question that might be in your mind is which of these 2 would be more acidic. And you can argue either way. You might say, well, since we're looking at an alkyl type substituent here, and an alkyl substituent would lower the acidity, and by inductive effect in the meta position it would make this one less acidic than this one. So you might predict it on that basis at least. Although I'll admit that's somewhat iffy, it does jibe with the experimental facts. And that gives you an idea of the different degrees of acidity, and in turn then the different degrees of reactivity of some of these OH groups. And it's quite a large difference, you see, all the way from a pK of 7, which is near neutral, and up to 14, which is less acidic than water. So that there is quite a range, and well overlapping. If we typical phenolic pKs 9 to 10, you see, well, you're well lower than that as well as considerably higher than that, so that the variability produced by the substitution is quite large. Now let's talk briefly about hydrogen bonding. I think we've already made the point that hydrogen bonds are stronger from the more acidic OH. So if we have an OH group like so. And the bond angle here is normally, I think it's 128 degrees. In any case, there is a rather specific bond angle that's the case, that is situation. And then it turns out that the hydrogen bond, that is the two non-hydrogen units that are linked by a hydrogen between, this is essentially a linear bond, needs to be a straight line. And then some other substitution, well, we might draw it more typical with a carbonyl, since the hydrogen acceptor group is apt to be nitrogen, oxygen, and a few others, but for our purposes mainly those two. And of course the more electron rich, since in this case they're sharing electrons or there's electronic attraction with the hydrogen, the more electron rich the structure, the stronger the bond, so that the dibonded oxygen, the carbonyl, would be a greater acceptor of hydrogen bonding than would the mono substituted, like say an OH. Nevertheless, an OH group, if this were another OH, we would still have a hydrogen bond attraction between the two. And it turns out that if you have a series, say you crystallize an alcohol, in the structure of the alcohol in the crystalline state, you find it's a linear series of polymerizations or hydrogen bond structures of that same general type. So you'd have a series of associations which would give a long fibrous type unit, which would be a subunit in the crystal, and that would be held that way in the crystal. So hydrogen bonding will occur between OH groups, with the hydrogen of one being associated with what you might visualize the backside of the oxygen of another OH group. But it's much stronger bond if it's a carbonyl, because the electron density would be greater. The double bond represents a concentration of electrons, and this would become then more negative-ish, and this would be the positive attraction. And although they're not strictly charged, the relative attraction would be in that order. Now, if that's true, then if we're talking about something equivalent to an attraction between a negative and a positive charge, then the more acidic this hydrogen is, the more positive it is, therefore the stronger the bond. And that's why hydrogen bonds within among phenols, or with hydrogens from phenolic OHs, are generally much stronger than from alcoholic units. And this then explains why the phenols become tannins, because this is the bonding that is primary in importance in associating a phenolic tannin with a carbonyl-bearing protein. The amide groups contain carbonyls, so that the tannin would be bound to the protein. Now, an individual hydrogen bond is a fairly weak structure, say 2 to 10 kilocalories per mole, whereas the covalent bond in your note says 60, although you can find them over quite a range. On the other hand, that would mean, say, from 6 to 30 hydrogen bonds would be equivalent to a covalent bond. And in a large tannin, you may have at least 10 OH, well, it wouldn't even be a large tannin with 10 OH groups. And if each of these is able to hydrogen bond, then in sum, you'd have the equivalent of a covalent bond, and therefore a very tight link between the polymeric polyphenol and the proteinaceous type molecule. And again, as I say, the more acidic then the hydrogen, the stronger the hydrogen bond. We might look at that in another way and say the more acidic this hydrogen is, what it really means is the less tightly held, and in fact you might say the longer the bond between the bonded oxygen and the hydrogen. And the further away, or the more nearly escaped is the hydrogen, then the more accessible it is and the more susceptible it is to association with another electronic center, and it gets to the condition where the hydrogen, you might say, hardly knows where it belongs. This bond is weakened, and this bond becomes relatively strengthened, and it's sort of oscillating or held between the two with a fairly strong attraction. Now, of course, you'd eliminate hydrogen bonding in an alkaline solution. In other words, if you ionize the hydrogen off, then the hydrogen bonding is not possible. So we're talking about in the unionized condition, the more acidic OH is attracted more strongly in a hydrogen bond type structure. And while we've drawn these as oxygen attractions, of course it can be attracted to other electron-rich centers like amino groups, other nitrogen-type structures, and in fact sulfur and a few others can be important in individual cases. But again, in the biological systems we're mainly concerned with, it would usually be the carbonyl-type structures. And it need to be kept in mind that the phenol then is the hydrogen donor in the bonding system, and the carbonyl is the hydrogen acceptor. And that has some important bearings from other viewpoints. Suppose we're going to talk about a partially oxidized phenolic system. Well, the simplest example that we can draw would be benzoquinone, which is the oxidized form of hydroquinone, and hydroquinone, of course, would be this structure. So if we oxidize this, we get this. But it turns out that in a mixture of these that have been exposed to air, it's rather easy to produce quinhydrone, and you may have heard of the quinhydrone electrode and so on. And quinhydrone behaves as if it were a compound. You can crystallize it. It has deep green colored crystals, and it behaves and has a melting point. It behaves just as if it were a compound. And quinhydrone is an equimolar mixture of the two forms where you have an oxidized phenol and an equal amount of the unoxidized form, and then hydrogen bonding of this type makes a dimer between them, and the two dimers are fairly specific, and you visualize, not as it's drawn here, it probably would be with the two rings facing each other. In that case, it'd be rotated out of the plane of the board, I think, and they'd fit nicely on top of each other and behave as if it were a compound. And the main point I want to be making here then is that as you oxidize phenols, you generate carbonyl compounds, so that then you produce the possibility of association between the not yet oxidized phenol and the oxidized derivative. And this is one reason why, as you oxidize things like wine, you tend to produce precipitates, because you'll find that the carbonyl structures generated will tend to associate with the not yet oxidized material and tend to fall out of solution. Now, there are other reasons they'll come out of solution too, but that's at least one reason, and helps illustrate why this kind of thing can be important. Now, we can have hydrogen bonds between molecules, as we've been discussing, but we can also have them within the same molecule, and this is the situation that we were illustrating in the case of the 5-OH and the flavonoids. So the flavones, at least, associated with the 4-keto group. So an internal hydrogen bonding would tend to prevent the OH from reacting externally in usual ways, whereas external hydrogen bonding may favorably influence such reactions. Now, how this can be studied, and it was mentioned in last class that there ought to be hydrogen bonding between nitro groups and the phenol, and then how come the nitro group favors acidic loss of the hydrogen ion? Well, again, the acidic character is overbalanced in that case, but it can be shown that there is hydrogen bonding in the nitro series. And how would one go about this? Well, it turns out that if you have strong hydrogen bonding, you affect the infrared structure of the OH band. So an OH group shows a typical absorption band in the infrared at about 1300, but this can vary up to around 3500 or so, and the reason it varies depends on how the hydrogen is held to the oxygen, because this is apparently an OH stretching type absorption in the infrared. And so we can study this by seeing how dilution affects the particular band, so that, for instance, if we make a potassium bromide disc and run an infrared spectrum, in the potassium bromide disc you would have a ground up solid matter, not perhaps exactly dissolved, and the KBR would be to some degree dispersing the crystalline form. something like a new Joel mull, say, particularly if you did a mull, you would find then you wouldn't be able to tell whether the hydrogen bonding was between molecules or within a molecule. But if you then ran a comparative spectrum in a solution like, say, chloroform and diluted it, then the more concentrated structure might show hydrogen bonding by the effect on this band, and as you diluted it, you'd get less and less hydrogen bonding if it's between molecules because you're diluting them, but if it's internal, then it would stay the same. So it turns out that if you do orthonitrophenol, the band is the same in both systems at about 3200. The meta form is about 3300 in KBr and 3500 in chloroform, showing dilution effect, and the para an even larger dilution effect. So by and large, then there's no internal hydrogen bonding in the para type, as you'd expect, a little bit, but very little in the meta position, and a great deal, so much so that dilution has no effect in the orthonitrophenol. At least this illustrates how one would go about showing whether that's true or not. Now, whether or not hydrogen bonding occurs can influence the kind of reaction that one gets. And I had the structure here I was going to write on, but I think it'll take a bit longer than it's worth. The main point being, suppose you had some internal hydrogen bonding and wanted to form, say, an ester group with that phenolic OH. If it's internally hydrogen bonded, it would be somewhat protected from this, and therefore you would not get easy esterification in the acid condition. You know, you commonly make esters by heating in a solution of sulfuric acid or something like that. Well, it would be difficult to make an ester this way because the internal hydrogen bonding would still be present. Whereas if you used an alkaline solution, like, say, acetic anhydride in a dilute alkaline solution, the alkali would disrupt the internal hydrogen bond, or at least might, and then you would be able to form esterification quite readily. And the example I was going to give you, you can direct the esterification depending on which way you would do the reaction. But I think that takes more time than it's worth. The main point being that the internal and external and hydrogen bonding in general can influence the course of reaction by making the OHs relatively inert or relatively strongly reactive in various conditions. Other examples are given on page 7 with the discussion of the distance of the bond. Now, we said ordinarily this bond needs to be linear, and if it's not linear, if there's some forced distortion from linearity, it weakens the hydrogen bond. And if that sort of thing can occur, if we're getting internal hydrogen bonding particularly. So for instance, suppose we had a structure like this with a carbonyl here. This can still be relatively linear. And the strength we've indicated is strong for that reason. But suppose we then had a 5-membered ring. Then this keto group would be forced away, and this bonding would become longer or more distorted, whichever way you would, so that it would tend to want to look this way, so that either this distance becomes longer or the bond becomes distorted. It will weaken the internal hydrogen bond. And this also will affect ionization effects and methylation effects and reactivity. And we have such examples. Now, it turns out not only can the 5-membered ring then make the distance longer, but if this were a 7-membered ring, it would tip the carbonyl in, and it would make the hydrogen bond stronger, so that 7-member rings would make perhaps the strongest hydrogen bond of the kind usually encountered anyway. The 6 would be strong, but slightly less, and the 5 or smaller membered rings would make the hydrogen bond rather weak. We won't spend much time on tautomerism, but it is important to mention that it can occur even in the phenol. And again, part of the reason for the name phenol is because it's like an enol. And the ultimate example of this would be the kind of structure that we've already drawn. If we visualize forming fluoroglucinol from 3 acetate units, you'd expect it to initially form in this fashion. Well, if it forms initially in this fashion, that's fluoroglucinol, but it would be keto-enol isomerized to this more usual presentation of fluoroglucinol. And it can be shown that there is a small amount of fluoroglucinol in this kind of structure by certain types of reactions. For instance, if we methylate fluoroglucinol in the presence of aqueous KOH and methyl iodide, we do produce some of the hexamethyl substituted type structure where we have methyl groups in these positions. So in the presence of KOH and methyl iodide, we get some of that sort of structure. Therefore, the molecule has to exist in a small percentage in the triketo type form instead of the phenolic form. These sorts of structures are generally quite transient, and the equilibrium is generally very far toward the phenolic form. Nevertheless, the fact that certain reactions require this condition is indicative of the fact that it can be an important function. Other types of reactions, for instance, if you react this with hydroxylamine, we can produce the oxime, which would be the substitution in the keto form. So you can show it is, in fact, the keto derivative. And by the way, these methyl substituted compounds then look kind of familiar if you think back on some of those that you were looking at in the ferns and in the hops for beer and so on. And while they're not formed quite the same way, obviously, in the biosynthetic sense, nevertheless, it does illustrate the fact that the keto form can be somewhat significant in forming the reactions. The way one could make some estimates in this direction, and what is more likely to happen, is that the estimate is that the keto form is ordinarily in the aliphatic series more stable than the enol form by about 18.6 kilocalories per mole, as your notes indicate. Now, we said that the benzene ring is more stable than the non-aromatic hexatriene type thing by 36 kilocalories per mole. And that should mean that if you can form at least 2 carbonyl types, you ought to be able to overcome the aromatic stabilization. Well, in the fluoroglucinol, we're forming 3. So on that basis, it makes it reasonable that the fluoroglucinol should be quite readily, compared to other phenols, converted to the keto tautomer. And that apparently is so, although these figures are a little bit do tend to overemphasize the possibility, because the inference would be that it favor the keto structure, and in fact it turns out that the percentage in the keto structure is quite small even for fluoroglucinol, but at least it is much more likely to form if there's at least 2 types of keto tautomers can form. Now, you should keep in mind that the keto tautomer now is not an oxidation product, even though it looks like it. In other words, we haven't lost any hydrogen in doing this keto-enol tautomerization. It's moved to a different position. If we hadn't methylated this, you see, the hydrogens would occur in these positions instead of on the one here and one here. But it's not an oxidized product, even though it tends to look like it. On the other hand, it is very easy for these compounds to lose substituents and become the equivalent then of an oxidized product. So that if you have an OH group, say we had more typically this sort of structure, where this is an OH and this is an OH, and then maybe a substituent like a sulfonic acid here, and we make the keto analog, meant to show it as aromatic. If we make the keto analog like so, then this is not oxidized, you see, but it's very easy to lose the elements of sulfurous acid, and this leaves, and then you have an aromatic, not an aromatic, but an oxidized product. It's equivalent of an oxidation, although it would occur by dehydration or sulfonic acid leaving from the structure. By the same token, if this were an OH, it would dehydrate readily. So then we would have a relatively oxidized type molecule and would in fact be a quinone, whereas in the tautomeric condition it isn't. This has some bearing because it's easy to make mistakes when you're looking at reactions and moving electrons around unless you quite understand whether or not an oxidation has occurred. Another point to be made here is since this kind of reaction is very easy in a naphthalene type situation, it means that one of these rings, if we call that one the A and the B, maybe that's backwards, but if we call this the A ring, it means this is in fact a little less aromatic apparently than this one. In other words, the total stabilization here is about 36 kilocalories, but it's something under that for the polycyclic unit, and this is illustrated even better if we look at the phenanthrene type analogs, because in the phenanthrene compounds we do find that the keto-enol isomerization is rather prevalent, and we have a fair amount of the structure in the anthrol type condition where this would have been a phenol isomerizes to the keto form and picks up an extra hydrogen and becomes an anthrol analog quite readily. And that would mean then that this ring is apparently a good deal less stable, less than 18, 19 kilocalories of aromatic stabilization, because this is no longer aromatic when you have this keto-enol type isomerization. And so by using such arguments, we can indicate something about the relative aromatic stabilization of different rings and possibly something about their reactivity. To give you an example, in page 8 under item 2 is a rather clear-cut example. Beta-hydrojuglone, which is found in green walnut hulls, in aqueous solution at room temperature, it's in equilibrium with a series of the half and completely enolized forms, ketolized or enolized in the full equilibrium. Now the ketone type is yellow, the substance is yellow, and the hydroquinone type is white or colorless, and if one extracts the solution with chloroform, you can extract the keto form from the solution, and you'll get a yellow chloroform solution leaving behind a white or colorless water solution. If you let the water solution sit around, it'll regenerate the yellow color, showing it's in equilibrium, and although you can crystallize the two forms separately, it does illustrate that both forms exist, and there is a fairly slow equilibrium between the two types, and certainly this then could influence reactivity. These sorts of structures may even be important, and under page 8, item 3, indicates the type of hydrated triketo structure that apparently has some validity in gallic acid. If you visualize gallic acid doing the same kind of thing as we discussed with fluoroglucinol, then we could lose the aromatic structure entirely and get the triketo form, but this is rather unstable, and in aqueous solution these would hydrate and you would get this sort of structure, and as drawn in your notes at least in those two positions. So this would be the triketohydrindine type structure, although we might want to do the same thing here. If you ever heard of triketohydrindine, have you heard of ninhydrin? Well, ninhydrin is a similar compound which is used to determine amino acids because it makes a purple color and so on. So these structures are not quite as exotic as they look. They're not too widespread, but they apparently do occur. And in certain hydrolyzable tannins, in order to explain some of the reactions and the structures, these sorts of gallic acid structures do seem to be necessary. And the book by Haslam that we've referred to you earlier would be a good place to see these sorts of structures being mentioned. I think these are the points that I wanted to make under keto-enol isomerization. This brings us to oxidation, perhaps the most important of the kinds of reactions. And oxidation, of course, does involve the removal of hydrogen or the removal of electrons. And if we visualize a phenolic structure, we can remove an electron, so we can remove electron in one stage, and then, of course, a second one, which would give the more stable oxidized structure. Now, if we remove one electron, and we usually remove the electron along with its hydrogen, so if we visualize the electronic arrangement in this form, then the usual oxidation involves the removal of the hydrogen and the electron, but it's usually done in two stages. Usually the hydrogen ion is removed first and then the electron second. Now that has some importance because it again comes back then to the idea that it's more easy to oxidize the phenolate ion than it is the phenol itself. If you're going to have to remove the hydrogen in the course of the oxidation of the phenol, then if it's already gone and you only have to remove the electron, then it's much easier to accomplish oxidation. So what this means then, if you have the solution more alkaline than the pK of the phenol, it'll oxidize very rapidly. If it's less acidic than the pK of the phenol, if it's more acidic, less alkaline than the pK of the phenol, it would be more difficult to oxidize it. If you, for instance, want to measure oxygen uptake in a wine and you put it in a Warburg, as I and my students have done, you'll find that it'll keep taking up oxygen for 2 or 3 weeks, and you'll be very tired of waiting for something useful to happen, and it becomes impossible to determine the end point because of experimental difficulties that arise over this long time. If, on the other hand, you make your Warburg flask, connect it to your manometer and so on, and tip in some alkali after you're all ready to go, it'll take up oxygen like you wouldn't believe. In fact, the first time I did it, I was kind of stupid, I guess, in retrospect, but it sucked the manometer fluid right back into the flask. It took up the oxygen like so, you see. So that in a matter of 5 minutes to 20 minutes, the reaction is complete if you make the solution alkaline, but it may take 2 weeks or longer and never seems to go to completion if you leave the solution acidic. And this, again, has important meaning in terms of analytical values, but it has other important meanings in the real world of browning and other oxidative reactions. For example, remember your titration curve, and while we drew, if we had a strong acid, we get this kind of a thing with the pK here. We don't have strong acids, we have very weak acids, which means that we have a very elongated, and that darn thing always comes in the wrong place. But if the pK is here, and this is pH of 9 on a typical phenol, but might be a good deal less for others, we still don't have 0 phenolate form until we get very low in pH. So it might take pH 1, or certainly at pH 3, we would have a small increment of phenolate ion present, considering the nature of the titration curve. And therefore, oxidation would be more and more rapid as you approach 9, and 9 and above would be in a very rapid, maximal rate. But even at the difference between 2 and 3, or 3 and 4, you would see a very great increment in reactivity as the pH rose. And this is extremely important in a number of cases. Take a simple example. If you have wines at natural pH of overripe grapes, which might be pH 4, then they'll oxidize much more rapidly and turn brown and throw pigments and polymers out of solution much more readily than a nice table wine at pH 3.2 or even a little less. So that this is an extremely important aspect. And again, if we're going to be most reactive in the phenolate form, then the most acidic phenol is the one that would be first oxidized because, or at least first in the phenolate form, so that it would be more readily converted to the phenolate form than the other. However, and we'll have to quit at this point, remember that you're removing an electron, so that whether it's more acidic or not will govern whether it's in the phenolate form, but it also has a bearing on how difficult, how much energy is necessary to remove an electron. So if it goes to the phenolate form quite readily, On the other hand, it means that the electrons are held rather firmly, so that you can't, you can generally make the proviso that the more acidic phenol would be in the phenolate form and therefore more readily oxidized, but on the other hand, the actual energy required for oxidation would be higher in the more acidic phenol. So as a consequence, often the less acidic phenol, if the solution is such it can be oxidized, the less acidic phenol would generally oxidize first. Unfortunately, I'll have to quit there. We'll